Так. Okay, then let us continue. What did we do last time? Last time we wanted to prove orbit-cone correspondence, and I think that we need to recall one part which was not well done. What if we take a cone sigma? We had a cone sigma, and we said that suppose that n sigma is the intersection, the linear span of the intersection, and n sigma in the brackets is when we quotient n by n sigma. So we use that, we have a non-degenerate pairing. Non-degenerate pairing between sigma orthogonal intersected with m and sigma to z. So I think I should explain it once more. We said that it was induced by the original pairing, by the pairing m to z. So how can we explain this? Let us take this sublattice. It has sense only in the case when dimension sigma is less than dimension of n. Otherwise it has no sense. It is all n, and this is only the 0 point. Okay, so in n sigma, and also using the normal Smith form and appropriate basis, we can say that n sigma we have basis A1, E1, etc. AK, EK. I explain right now why the quotients A1, etc., AK are equal to 1. Okay? N basis E1, etc., En. So if there are some AI which are not equal to 1, we can consider a point in sigma, which is its interior point, which is far away from 0. And so in this case, if we take some let the combination of these vectors be the interior point, if it is far away from 0, we can subtract E1 remaining in sigma. And so it shows that AI are equal to 1. Is it clear? If we say that n sigma is generated by some multiples of basis vectors, but on the other hand, if we have a vector, we have all the vectors which differ by EI. Is it clear? Since I mean, we have sigma in the lattice n. This is our vector, this is our cone sigma. If we have some interior point such that its distance to the boundary of this cone is greater than the length of basis vectors. Okay? If we have some vector v in sigma, what is n sigma by definition? It is this intersection. if we take V minus E1, it will be in N, it will still be in N, and it will be in sigma, since we asked the distance to be at least 1. Okay? And it will contradict the fact that N sigma is generated by A1, E1. If N sigma is generated by these vectors, then all the elements of N sigma are combinations of these vectors, and all the coefficients at E1 are divisible by A1. And so this shows that A1 equals 1, and so on, AK equals 1.
Why?
In the same way, we can consider vector V minus EK.
No, that's
Yeah.
I mean, what's so yeah, V in sigma, V. What if there is no V that has length to each border?
No, we can't take any interior point of the cone. We can take its multiple far away from 0.
Okay.
If it is an interior point, it has the smallest distance to the boundary.
Yes.
And if we multiply it to some k, it will be far away from the boundary.
Yes.
I just say that from this construction, it follows that the lattice inside sigma is in fact the same as n. It is part of n. It cannot have coefficients here. Согласованные базисы. Еще раз, у нас есть решетка n сигма и решетка n. У них есть согласованные базисы. Было дело? Вот я пишу эти согласованные базисы. В смысле, это базис n такой, что базисом под решетки являются вот такие векторы. Да. So first of all, we find the appropriate basis, and then we show that all AI equal 1. Okay, we show that all AI equal 1, and now it is more or less clear that in this case, so sigma orthogonal is we can say that it has basis. It has basis EK plus 1 dual, etc. En dual. We have a basis in N. So in M it has the dual basis. And now clearly, if sigma is generated by some linear combinations of these vectors, not necessarily by E1, E2, etc., Ek, but by some vectors which are linear combinations of these vectors such that they are linearly independent. So sigma dual will, no, sigma orthogonal will be all the linear functions which vanish on these linear combinations. So it will not contain E1 star, etc., Ek star. Is it clear? Okay. And all these vectors are indeed in sigma orthogonal. And now clearly this is generated by Ek plus 1 star, etc., En star. And this is just the quotient. And the quotient is generated, we can consider it as it is generated by Ek plus 1, etc., En. So we have dual bases here, and we have a Z linear pairing. We are done with the first part. And should I repeat the end of the proof from the last time? About O sigma.
Yeah.
Okay, last time about O sigma. So we said that we want to explain why O sigma is the torus orbit of the point Tn applied to gamma sigma. We wanted to prove this. Yeah? What was our idea? We take O prime, which is just the union of all semi-group all morphisms from sigma orthogonal intersected with M, and C star, all Z linear maps. Okay? We also know from this that we have a surjective map from N to N sigma. So we have N which maps to N sigma. One more moment. We know that the torus which acts here, the torus is the tensor product of this lattice with C star. If we have this, then we have Tn. It maps surjectively to T n sigma. Okay? And what is O prime? This is the set of all maps from this which do not vanish. This is a maximal linear subspace of sigma dual, and we take all the maps from this space to C star. But now we know that this is isomorphic to the torus. So we can say that T n sigma is the same as hom z this stuff. And we know that the big torus acts on both sides. It acts here and it acts here. We wrote it last time. We multiplied these maps to some non-zero value. Okay. So we know that the big torus Tn acts transitively on.
Can I ask you a question about this word?
Yes.
What we proved? What we have proved this for?
We wrote explicitly that this quotient is a free abelian group, and this is its dual. So it is a free abelian subgroup, so a lattice, and this is its dual lattice.
So we just proved that this is non-degenerate firing. Yeah.
But now we know explicitly that these are two lattices and they're dual. It is clear that this is a lattice, but by construction, it is not so evident that this is a lattice.
Yes.
So in this proof, I explained why it is a lattice. And so if it is a lattice, I say that the corresponding torus is its tensor product. It's homomorphisms from this to C star, as we did in the very beginning. Okay. Once more, we know that this is a torus, and we know that Tn maps to it surjectively. So this acts on this transitively, because if we have two non-vanishing maps from this to this, we can take their quotient, and this will be the necessary element of the torus. we just find an explicit element of this torus which maps the two homomorphisms from this space to this chart, one to another. Okay, so we conclude that Tn, the big torus of our toric variety, it acts transitively on O prime. What else? We know that gamma sigma belongs to O prime because gamma sigma is the concrete map which maps all this to 1. Do you recall it? Okay, so gamma sigma belongs to O prime. What else? It is in O prime. O prime cannot split into more than one orbit of the big torus. And it contains, O prime contains Tn gamma sigma, so they will coincide. We conclude that O prime coincides with O sigma, which by definition was Tn gamma sigma.
Yeah, why Tn acts transitively? Can you repeat this?
Yes, Tn maps surjectively to this stuff. Just because we have a surjective map of lattices, and so the toric also maps surjectively. And Tn sigma acts on O prime transitively because we can show how to map one element to another.
Just because it's n sigma is due to sigma orthogonal intersection.
No, I'd prefer if we have 2 points of O prime, each point is a homomorphism. Okay? We can take the quotient. At each point of this subspace, we have the value of one homomorphism divided by the value of the other homomorphism. If we shift them by the corresponding element of the torus, they will map one to another. Давайте я по-русски скажу. Еще раз. Что такое точки О'? Это морфизмы из вот этого какого-то из этой подрешеточки небольшой в С со звездой. Дальше, как Тор действовал у нас на О'? Как Тор действовал на О'? Мы запихивали вот сюда вот это число. Ну, то есть просто умножали, да. И поэтому, если у нас есть два разных гомоморфизма, они в С со звездой, они в С, то мы можем как бы на порождающих посмотреть и посмотреть на порождающих, как бы, как именно должен действовать Тор, чтобы одно в другое перевести. Просто подобрать числа на порождающих, и дальше на всех остальных элементах тоже достроить. Вот и все. Okay, so the torus acts transitively on O prime. O prime contains at least one orbit O sigma. So O prime is exactly this orbit O sigma. O prime is T invariant. So if it contains this point, it contains the whole orbit. Okay, do you agree? Okay, wonderful. And now we can prove the orbit cone correspondence. Okay. I think I should recall the statement, maybe one by one. We formulated it last time. The orbit cone correspondence. but I have, unfortunately, different books have different notation. Today I will use the sigma for a fan. So let sigma be a fan, sigma and not delta. So X sigma is the corresponding toric variety. Does everybody remember how do we construct X sigma? Okay. Then the orbit cone correspondence, I will prove 4 statements today. The first 2 are the following. There is a bijective correspondence between cones in our fan and between T and orbits in X sigma. So for sigma, we construct the orbit O sigma, which is isomorphic to Hom Z sigma orthogonal intersected with M and C star. And if N is dimension of N, then the dimension O sigma equals N minus the dimension of sigma. Okay, let us prove it. First of all, take we know already how to construct an orbit O sigma if we take sigma. We explained it right now. Given a sigma, how to construct O sigma. We show the other direction. So proof of 1 in this direction. Let O in our toric variety be a T and an orbit. So we know that our toric variety is glued up of affine charts. X sigma is covered by U sigma. We have many different notations. U sigma is the affine toric variety. This is open in our variety X, and it has full dimension. It is covered by U sigma. We know that all U sigma are torus invariant. So if our orbit belongs to U sigma 1 and also to U sigma 2, we can say that it belongs to U sigma 1 intersected with sigma 2. Okay? Just by construction, we know that this intersection is U sigma 1 intersected with sigma 2. And so there is a unique minimal cone in our fan. Sigma and sigma such that O belongs to U sigma. Let us prove that O equals O sigma. So, is it clear? We take one torus orbit. Since our variety is covered by its affine charts, and each affine chart is torus invariant, then if two charts intersect and our orbit is in them both, it is in this chart, and there's a minimal sigma with this condition. Okay. Now, for this, we take a point gamma in this orbit, and consider we know that each point is in fact a map from, since O is in U sigma, we have maps from sigma dual intersected with M to this is from this to C. Okay.
Isn't there should be exist maximal sigma in fact, since we have since maximal sigma is
No.
minimal u sigma.
No. So if O is the torus which acts, it will mean that it will belong to all U sigma, and the intersection of all U sigma is the torus which corresponds to the origin.
Yeah, but I don't understand if all seeds in U sigma 1 intersect with U sigma 2, all seeds in U sigma 1 and in U sigma 2, so we can...
Our aim is to find a minimal sigma. I mean, if here O is a torus orbit which is the whole torus,
So
we will take the origin. Okay, so gamma is some map, and we can take all M such that gamma of M is non-zero. I think I should draw a picture here. I don't want to prove it right now. I think it's a good problem for the seminar. So what does it mean? We have sigma dual, and we have some semi-group homomorphism. So all the points where it doesn't vanish, it is a face of this cone. Such M form a face. Is it clear, more or less? We cannot have that some for some points here gamma of M is non-zero, and on the left-hand side and on the right-hand side it is 0. It will not be a semi-group homomorphism. Is it more or less clear? Yes. Form a face of sigma dual. Mm-hmm.
No, but probably it's true.
Okay, we have sigma dual, and we have a semigroup homomorphism to C. It cannot be so that at some point it is 0, and on the left hand side and on the right hand side it will be 0. It is not a semigroup homomorphism, because this multiplied by this will be the square of this.
Okay.
So if it is everywhere non-zero, we have such M form the entire sigma check. If there are some points where gamma vanishes, then it will be all but some phase. We will prove this on the seminar. It is not quite difficult, it is more or less technical. Okay. But we know that all the faces of sigma check are of the form sigma check intersected with a tau dual. And if we have this for some non-trivial tau, it will be in fact a semigroup homomorphism from tau check, and it will be this point will be in O tau. Not in O tau, it will be in U tau. If Gao belongs to U tau. Sigma was minimal. It means that tau equals sigma. And we have that now this is indeed O sigma. So each point gamma is a map from sigma check intersected with M to C star, and it doesn't vanish. Gao belongs to C star for each M. And so all gamma belong to O sigma. We have the description of O sigma.
Why gamma belongs to U tau?
If we have a phase, then it means that we map all this to C star.
Yes.
Okay, so tau orthogonal is the maximal linear subspace in sigma check, in tau check.
Yes.
So what is U tau? It is all the semigroup homomorphisms from tau check to C. Yes, and they're semigroup homomorphisms, so we need to send the tau orthogonal to some non-zero elements. So in fact, each morphism of this kind can be extended to a morphism of tau check. So is an element of O tau. Okay. Okay, and we are done. Because we know that all such gamma, they send sigma check to C star, they are elements of this torus. And so they contain gamma sigma and they contain its orbit. So we proved 1. Now let us prove 2.
Isn't we proved 1? Only the 1.
We said that this direction is already done. For each cone sigma, we have the distinguished point, and for this distinguished point, we can take its torus orbit, which will be exactly O sigma.
Yeah.
And we proved that its torus is of this form.
Okay.
1 is done, and 2 is obvious. It follows from this explanation. What is dimension of sigma? Dimension of sigma is k in this notation. And the dimension of the torus is n minus k. And we are done. Да.
С каждым конусом сопоставлять, получается, и карты, и...
Чего только не сопоставляется, да. Сейчас будет еще.
Вот вопрос, вот эта
Да.
орбита соответствующая, она лежит в этой карте или как? Или
Да, конечно, она в ней лежит. Орбита лежит в карте. Ну, смотрите, потому что такое карта? Это все полугрупповые гомоморфизмы из сигма двойственного в С. Ну, то есть, по сути, это как бы координатные функции. Среди характеров есть координатные функции. А полугрупповой морфизм, это означает, что вот если вы на каких-то координатах ее задали, то на всех остальных вы ее досчитаете. Вот. А орбита, она же должна быть как бы тором, это то, где в целом все они не нулевые. Ну вот как бы, как задается тор в n-мерном пространстве? Стандартный n-мерный тор в n-мерном пространстве. У него все n-координаты не нулевые. То тут у вас примерно то же самое получается, что у вас О сигма это вот как бы гомоморфизм в С со звездой. Сейчас как правильно сказать? Не, ну все, да, это его решетка. Это решетка, все не в ноль отображается.
просто эта орбита наша меньшая размерность.
Да, вы правы, ну, потому что это часть координат. Да, смотрите, вот у вас есть подрешетка, порожденная вот этими штуками, да? Про Е1 со звездой, Е2 со звездой и так далее, ЕК со звездой вы ничего не говорите. То можете отображать куда угодно. А вот эти отображать строго не в ноль.
Хорошо, понятно.
Да. Правильно? Нет, неправильно, потому что как раз наоборот, про те вы их отображаете в ноль.
Ну да, те в ноль, а эти всегда не ноль.
Да, я на самом деле обманула. Вот эти всегда не в ноль отображаются, потому что когда у конуса сигма двойственная есть конек, то элементы конька вы вынуждены отображать не в ноль. Но все, значит, все у сигма это то, где вы вот эти отображаете не в ноль, а вот эти куда угодно. А орбита это когда вы вот эти отображаете не в ноль, а эти в ноль. Ну вот эти вот в ноль. Е1 со звездой или ЕК со звездой. Так, хорошо. Тогда in the orbit correspondence last time I stated 4 statements. The third one and the fourth one are about U sigma and about the closure of the orbit. So what is the third part? The third is that U sigma is the union of orbits O tau for the faces of sigma. Tau is a face of sigma. So it contains the torus. The torus is for tau 0. So how do we prove this? And maybe I write 4. 4 is that tau is a face of sigma is equivalent to the fact that O sigma is in O tau bar and O tau bar is the union of for all the faces tau of sigma O sigma, where the closure can be taken both in classical and the Riesky topology. So I think I will prove the classical case just to gain some time. Okay. How to prove 3? We know that that U sigma is invariant, so it is a union of orbits. U sigma is a union of orbits.
Why is it invariant?
It is the affine toric variety.
Oh.
We know how torus acts on it. Yes. And if tau is a face of sigma, we showed that O tau is in U tau, which is in U sigma. Okay? The next step. We showed here that each orbit corresponds to some face of our to some cone of our fan. Yeah. Each orbit corresponds to some tau in sigma. We can show that tau is a face of sigma. Why? Because if we know that each orbit is a map from tau dual to C. No. And we know that, since we know that it is already a map from sigma dual, we should have that it contains sigma dual. So we know that this orbit O tau belongs to U sigma. It means that each point of it is a map from sigma check to C. It implies that it is technical. We can also do this in the seminar, since it is a map from sigma check and also from tau check. We need this inclusion, and then we get that tau is always a phase of sigma. And now let us prove the last statement in classical topology. Let us take O tau bar for some cone tau, and we know that it is torus invariant. It is Tn invariant because if a point of the closure is a limit of some points in the orbit O tau, then we can act by the torus, and any other point of O tau bar will also be in. So if we act by T on any point of this, it will also belong to the closure. Okay. So I say that if I take O tau bar in the classical topology, it will be a torus invariant. Because if we have a sequence of points which converge to some point of the closure, then if we act by the torus on this sequence of points, yeah, they are also in O tau, and their limit will exist, and it will be another point of O tau bar. Okay. So it will be a union of orbits. Okay. Let us suppose that some orbit O sigma forms part of O tau bar. In this case, we can write that O tau sits in U sigma, since otherwise we have O tau intersected with U sigma is empty, this is one orbit, this is many orbits. Either it is in this set or they don't intersect, and if they don't intersect, this is open in the classical topology. So if this intersection is empty, then O tau bar intersected with U sigma will also be empty. Okay. So if this is true, then by this we by 3 tau is a phase of sigma. Yes. And conversely, let us show that for each phase tau, we have this. If sigma is such that tau is its phase, then O tau is in the, no. Yeah, then O sigma is in the closure of O tau. I will erase points 1 and 2. So tau is the phase of sigma. So for this we will use limit points. We want to prove that O sigma is an O tau bar. So as above, we want to show that O tau bar. Just by the idea is that this is a union of orbits. We want to show that this intersection with O sigma is not empty. Okay? And we use limit points. We take the distinguished point gamma tau, this is the point which maps some monomial to 1 and all the others to 0. Okay. And take U from the relative interior of sigma. And for each T from C star, we take the curve, we define gamma T is M is mapped to chi M of lambda U of T gamma tau of M. Okay, and this is in fact T mu gamma tau of m. So this is a curve which is in O tau for all t, for all non-zero t. Okay, and now let t tend to 0. T tend to 0. So we know that we took u from the relative interior. So u. It means that mu will be positive for m in sigma check without sigma orthogonal, and it will be 0 for m from sigma orthogonal. Okay? And by all this, we know that the limit when t tends to 0 of gamma of t, it will be some semigroup morphism. It will be a point of u sigma, because it will be correctly defined on sigma check. Once more, we have gamma t. It is a morphism from some part of lattice M to, here we have a morphism to C star. When we take the limit, it can become a morphism to C. It is bounded on sigma check. It will be either, the limit here will be either 0 or 1. So the limit exists on sigma check, and it will be a point of u sigma. And we are done. The intersection is non-empty. The intersection here is non-empty. And we are done. If it is non-empty, then O sigma belongs to O tau bar. Okay. We proved more or less the orbit-cone correspondence. And I think if I have time, I want to prove the compactness criterion for toric varieties. I think I will have no time for all the details, but I will try. And who wants to stay for the seminar? Okay. Hmm?
That's sad.
Okay. Then we have time till 6:30.
Yeah.
Okay. The compactness criterion. Okay, we take a fan sigma. We have 3 equivalent conditions. the equivalent conditions. First is that X sigma is compact in the classical topology. Then the second is that the limit lambda u of t when t tends to 0 exists in X sigma for each u from n. And the third condition, the most combinatorial, is that the fan is complete, which means the union of all the cones is the whole space. I think I can give an example of what is a complete fan. A complete fan, for example, is this fan, which corresponds to P2. Or you can subdivide it in any way, and this will be a complete fan. Okay. We formulate three conditions for the toric variety to be compact. And for us, compact is that every sequence of points has a convergent subsequence. So this is quite long, but I hope that we have time for it to prove that all these conditions are equivalent. So let us start. First, A implies B. So let us fix U in N. And we assume that X sigma is compact. We want to show that this limit exists for each u. We take a sequence of t's tending to 0, t1, tk tending to 0. Tk non-zero. We get a sequence of points. We get lambda u of tk. We know that since X sigma is compact, this sequence has a convergent subsequence. Okay. And we can assume that so it converges to some gamma in X sigma. We may assume that gamma belongs to U sigma for some sigma, since our toric variety is covered by these affine charts. Okay. Now we can take M from, if we fix this sigma, what does it mean? M belongs to sigma check in M. So this is a regular function on U sigma. The corresponding character is a regular function on U sigma, and hence it is continuous. In this case, we have chi m of gamma, but gamma is our limit point. So it is limit for when k tends to infinity of chi m over of this stuff of lambda u tk. But we know how to find this. This is the pairing between characters and one parameter subgroups. U is from n, m is from m, and as usually this will be tk power, this was the limit, tk mu. So we know what is mu, and we know that tk tends to 0. We conclude that mu is non-negative for all m in sigma check. And so U is from sigma. Should I explain?
This is not for TK, for subsequence, yeah?
We forgot about the initial sequence. From this point, we take a it has a convergence subsequence. From this moment, we forget all the other points.
Yeah, but how we understand that it converges? Is that it has a limit?
Yes, I mean, we know that X sigma is compact. We take a sequence of t tending to 0, yeah, and we fix some u. So we have a sequence of points. It has a convergence subsequence. Forget another ti. At this point, we just keep only those ti which correspond to our convergence subsequence.
Yeah, but we want to understand that it has a limit.
We will no initial. We want to show that for each u from the lattice, there is the limit when t tends to 0.
Yes.
Just this is the curve.
Yeah, but if we forgot about the other things,
It
has
is just a technical
convergence of sequence,
Yes,
then the
I mean-
gamma is already the limit.
for us, the sequence of non-zero complex numbers is just a technical stuff.
Yeah, I understand, but
We haven't finished yet. This is just a conclusion.
no,
That-
I just don't understand. Вот смотрите,
Да,
вы берете последовательность, да, какую-то, которая там стремится к нулю. окей?
да,
Берете лямбда у от этой последовательности
Да.
и берете там сходящуюся последовательность.
да.
Так мы хотели сказать, что последовательность сходится, а вы говорите, что мы забываем. Ну, мы же хотим
Не-не-не,
сказать, что
нет, еще раз. Вот это не последовательность. Это просто предел написан. Там k стремится к бесконечности, а тут t стремится к нулю. Это некая кривая. Эта кривая, она лежит в многообразии x сигма. Но как бы у нас были разные кривые. Некоторые кривые убегают на бесконечность, например,
Да.
а у некоторых кривых, наоборот, есть предельная точка.
Ага, ну ладно, да.
То есть это кривая, а это просто последовательность точек тупо. Потому что сейчас мы предполагаем мы предполагаем, что x сигма компактно. В нашем, как бы, мы считаем, что компактно это то, где есть у любой последовательности есть сходящаяся подпоследовательность.
Ну да.
Там у нас у Хаусдорфа все хорошо.
Ну,
Да. Значит, еще раз, пока это некое техническое преобразование, мы получили некий результат. Once more, we took a limit point. We assumed that this limit point belongs to the open chart U sigma. And then we get a conclusion that in this case U belongs to sigma. Okay. Maybe this was rapid. I took any m from sigma check. I showed that this is true, and then U belongs to sigma check check, which is sigma. Okay. But we know that if U is in sigma, then the limit, we proved this last time, I think. In this case, U is in sigma, then the limit when t tends to 0, lambda ut exists in U sigma. In U sigma, and hence in the whole variety X sigma. So we have proved A to B. Now B to C. Our aim is to prove that the fan is complete. For each U, this limit exists if and only if U in sigma. But each lattice point of our n of n r belongs to some sigma, but the same stuff as here. And so sigma should be complete. Okay?
why do we have that each lattice point of the
Once more.
basis?
Yes. Last time we proved that if U is not in sigma, then the limit in U sigma doesn't exist. So if we have some U which is if we have some bad fan, this is a bad fan, and this U is not covered. So for this U, the limit point, it cannot exist neither to this affine chart, nor to this, nor to this, because we take some product of this form, and for each affine chart we have that this power will be negative and t tends to 0. We did this last time. We showed that if this is a cone and a point which is not in this cone, then the limit doesn't exist because it tends to infinity. So B to C is quite easy. And now C to A is the most difficult and the most technical. C to A. This is by induction on the dimension of induction on N, which is dimension and R. Okay. Unfortunately, I have to use something from the sheet which will appear soon. So the star construction. How to construct a fan for the torus orbit closure. Star. It means that we take all the cones which contain some sub sigma. We take all the cones which contain sigma, and then we take the space n quotiented by and intersected with the sigma, and we construct a new fan in this space. So in the sheet, you will have the problem that if sigma was complete, then star sigma also complete. I think it is more or less clear. If you have a fan which covers the whole space, and then you take some cone of smaller dimension, then if you quotient by this by the corresponding subspace, you will also get the entire space. You need some accuracy because in this definition you take only the cones that contain sigma, but in the quotient space they will cover the whole quotient space. Okay, and now let us prove this statement by induction. The base of induction is n equals 1. How many complete fans in dimension 1 do we have? This is our fan, and the corresponding variety is P1, and it is compact. And we are done. Now, suppose that we proved that if the fan is complete, then the variety is compact. We proved C to A for all dimensions less or equal than n minus 1. And now we want to prove for dimension n. We take a sequence in our variety x sigma, and we want to find a convergence subsequence. Take a sequence of points gamma k of points of x sigma and sig for a convergent subsequence. So we know that x sigma is the union of orbits, is a finite union of orbits by the orbit cone correspondence. And so without loss of generality, we may assume that gamma k is in one orbit. One moment. We can say that there is one orbit which contains an infinite number of our points.
Oh, so it's finite, yeah.
Yeah. Okay. So all gamma k are accumulated in one torus orbit. And we want to find a limit point. But if if tau is not the origin, then dim O tau, it is equal to the dim O tau bar, it is less than n. If dimension of tau is at least 1, then this dimension is at most n minus 1. And O tau bar is a toric variety corresponding to the fan star tau. Okay, this is what I constructed at the left board. All the cones containing tau, and we treat them in the quotient space and quotiented by the span of tau. It has a smaller dimension. It is a toric variety. So each convergent, each infinite sequence has a limit point. And it also lives in the initial toric variety. So in this case, if tau is not the origin, we are done. And the only case which remains is when all points belong to the torus. Okay. Some more work. I erase this. Assume that all gamma k belong to Tn. And what is Tn? Which is isomorphic to home Z from M to C star. Each element of the torus T is a map from M to C star. Okay, now we take a logarithm. What is a logarithm? It maps from the torus Tn is mapped to the real numbers. We take the logarithm of the absolute value of gamma m. This is just the definition. This is a homomorphism.
What is gamma?
Gamma is a point of Tn. By our construction, each element of torus is a map from M to C star.
Yes, so we take M and it goes to how
Okay,
N
there.
acts on Tn.
One moment.
This is action.
I explain. There are some coordinates on the torus. Okay? And for each coordinate, just gamma m is the value of its coordinate. If m is a coordinate
M is element of what?
of m,
Aha, so then there is a wrong. There's something wrong. Like
Why?
L is a map from what to what?
from the torus to the real numbers.
Aha, so then
That's okay.
M is an element of M.
Tn is the set of homomorphisms.
Okay.
If you take some homomorphism from
So what is L of gamma?
L of gamma, gamma is how we map all m.
Yes.
You can restrict yourself to the coordinate monomials.
Okay.
For each coordinate monomial, you compute this stuff.
What is gamma?
This is this map from M to C star.
Okay. So L acts. So L transforms gamma to what? To some element of R.
No, gamma is fixed. You fix some gamma.
So it's L lower index gamma. Something like that. Or what?
Okay, L gamma. It maps M to this.
Okay, but M is not an element of the Tn.
It is a monomial.
So it should be something like chi M.
We say that gamma is the semigroup homomorphism.
Gamma is semigroup homomorphism. Okay.
So just you take some non-zero value.
Yeah.
You take its absolute value.
L gamma should act on element of Tn.
No,
Why?
no, gamma. Okay, gamma 1, gamma 2 belong to Tn.
Yes.
So for each for each gamma, this is a linear map from Tn to R. I mean, if you take L gamma 1, gamma 2 is L gamma 1 plus L gamma 2.
What is L gamma 1? How it acts on Tn?
No, it doesn't act on T, it acts on M.
L gamma is the morphin from Tn to R. So it should act, it should transform some element of Tn to element of R.
uh, uh, maybe we should take the power n here. Okay.
Okay.
I mean,
gamma goes to a logarithm of gamma of m1, logarithm of gamma of m2, where m1 and 2mn is just
it's just the basis.
basis. Okay.
Okay. If we take two different gammas,
Okay.
if we so they're elements of torus, we can multiply them. If we multiply them, then we multiply all the basis monomials, and then we have that we should sum up them. Okay, and so this is each L gamma is an element. L gamma is an element of Hom Z from M to R. Okay? And this is
Why?
just if we look how it acts on M. Just for each coordinate monomial, we explain that this is this logarithm. And for the product of coordinate monomials, we just take the sum. M is generated by the coordinate monomials.
Yes.
And for the product of some monomials, when we take logarithm here, it just becomes the sum of the corresponding logarithms.
So what? So L gamma of m is just the logarithm of modulo of gamma m. Yes.
Yes.
Okay.
Yes. And so we obtain this. We obtain this, and which is in fact NR. They are dual lattices. Okay. We defined L gamma, and now we need some properties. Suppose, so we assume this. Suppose that some gamma of the torus Tn satisfies in this construction. We constructed L gamma, and we explained why L gamma is an element of NR. And suppose that it is L gamma is in the minus sigma. I mean, we have a fan. We make the central symmetry. If this is the initial fan, we draw another complete fan just in this way. It is also complete. And we take such sigma for which L gamma is in minus sigma. L gamma can be treated as an element of NR. Okay. Now if we take M from sigma dual intersected with M, then by definition logarithm gamma m we said that this is a linear functional, so it is the pairing M and L gamma. Just since it is a linear map, it can be written in this way. And we have M from sigma dual and L gamma from minus sigma. Then this is non-negative for each M from this. This is not the end. We conclude here that the absolute value of gamma M is at most 1. I think I erased this. The absolute value of gamma M is not more than 1. Okay, what is our aim? To show that our sequence of points which belong to the torus, that they have a limit point. Okay, what next? What next? This is true for all M in sigma check with M. Okay. Now recall that we have a sequence of points gamma 1, etc., gamma k, etc. We can logarithm all those points. Take this sequence. Gamma k. So by passing to a subsequence, all these points, they belong to n. And n is splitted to some cones in this way. So we assume that there exists a sigma such that the corresponding points of n, L of gamma k, belong to minus sigma for all k. What next? We say that for all monomials from this, their values will be bounded for all k. Oh, okay. For all k and for all m from sigma check, we have gamma m is not more than 1. What does it mean? We have some coordinate monomials, and all the coordinates, all the n coordinate map to the product of n disks. N unit disks in C. Okay? So this is a condition that some coordinate is in the unit disk. And now there is a subsequence which converges to some point. ну, как вам удобно будет? В смысле? Ну, ну, сейчас, еще раз. Гамма m это одно комплексное число. То есть я на это хочу смотреть так. У нас есть решетка m, у нее есть порождающие. То есть для каждой... нет, не решетка m. Давайте так, полугруппа m, да? У этой полугруппы есть порождающие. Ну, не n, а какое-то конечное число. Еще раз. Есть порождающие полугруппы. Я знаю, что для всех порождающих полугруппы по модулю это значение ограничено. И поэтому, по сути, то есть мое отображение точек это в компакт. Что я хотела? Я хотела показать, что есть сходящаяся подпоследовательность. Если, значит, все мономы сходятся, то и точки сходятся. А если у меня, значит, логарифмы всех этих гамма m сходятся, то сейчас, если все гамма m сидят в диске, я выбрала сходящуюся последовательность, значит, все гамма m к чему-то сходятся. И, значит, у Тора все координаты совпали. На Торе у этого будет предельная точка. И все, победили. So there is a subsequence which converges to a point in U sigma. So we are done with this criterion, and I think that that's enough for today. Any questions? Mm-hmm. Хорошо, ладно. Тогда надо остановить трансляцию, да?
Ну вот, есть кнопка «Остановить трансляцию».
А, на ноутбуке, хорошо.